What if I told you that the absolute smartest, most mathematically perfect way to solve a problem is actually the worst thing you can do for your
Yeah,
software?
yeah. It happens all the time.
Right. I mean, we have this deeply ingrained assumption that optimizing a process, whether that's your morning routine or a team workflow or, a piece of code, means you have to make it more complex.
Exactly. We think we have to outsmart the system, strip away every inefficiency by hand, and build this rigid, highly engineered highway.
Yeah, but welcome to the deep dive, everyone. Our mission today is to unpack that exact tension.
We're looking at the very frustrating collision between theoretical optimization, actual real-world performance, and just, well, plain old human readability.
And you really don't need to be a software engineer to relate to this. The core dilemma here applies to anyone who's ever tried to find the quote-unquote best practice for a problem, only to discover it made their life infinitely harder.
So true. We're anchoring this in a fascinating piece of source material published today, July 31st, 2026.
Hot off the presses.
Right. It's a blog post by a developer named Ang titled Notes-on-Haskell-Programming, Part 201, List-Comprehensions versus Fold.
Now wait, I know Haskell programming might sound incredibly niche if you don't write code for a living, but stick with us.
The stakes here are universally applicable.
They really are. We're going to examine a deceptively basic task, literally just counting items in a list, and discover how a highly recommended, theoretically flawless refactoring suggestion actually backfired spectacularly.
Yeah, to understand the magnitude of that failure, we kind of have to establish the baseline first. We need to look at the original code Ang was working with.
Right, the setup.
Yeah.
So Ang was dealing with text processing on a massive scale. The system processes large novels, texts with thousands upon thousands of chapters.
And the goal was simple enough, right? Ang has this enormous data set, a list called blocks, that contains all the structural elements of a novel.
So paragraphs, chapter titles, footnotes, everything.
Exactly. And Ang just needed to filter through that massive list, isolate the specific headers that represent a volume, and count how many there are.
So let's look at the mechanics of that first attempt. The original code used a feature called a list comprehension.
Right. Functionally, it tells the computer to walk through the entire blocks list, examine every single item, and filter out anything that is not a volume header.
Which, I mean, that makes logical sense. You have a pile of data, you isolate the data you want.
Yeah, perfectly intuitive.
Looking at the code in the post, Ang writes this out using a structure that basically says, give me the length of this specific subset of blocks.
But there is a very peculiar detail in there.
Yeah, instead of keeping the actual text of the volume header, Ang uses a placeholder. It's represented by two empty parentheses.
Right. That is the unit type in Haskell. It essentially means nothing of interest here.
Just a blank.
Exactly. Because Ang only cares about the final count, not the title of the volume or the text inside it. There is no reason to store the actual data.
So what does the system do?
Well, for every volume header it finds, it creates a brand new intermediate list in the computer's memory and populates it with one of those empty unit placeholders.
So it builds a new list of dummy items.
Precisely. If it finds 50 volume headers, it constructs a new list containing 50 empty parentheses.
Okay.
Then, in the second step of the process, it uses a length function to walk down that newly created list and count the placeholders. 1, 2, 3, all the way to 50.
I have to put myself in the shoes of someone looking at this from the outside, because building an entirely new list just to count things feels incredibly wasteful.
Oh, it absolutely is.
It's like wanting to know how many chairs you own. So you rent a moving van, drive all your chairs across town to a brand new empty house, line them up in the living room, count them, and then burn the house down.
That is a great way to picture it.
I mean, why move the data at all just to tally it up?
And that scale of wasted effort is exactly where the problem lives. For a small pamphlet, moving a few chairs across town happens so fast you don't even notice it.
Right.
But Ang is dealing with massive novels. Building an intermediate list of 10,000 dummy items consumes a very real, tangible chunk of the computer's memory.
And the hidden cost there isn't just the memory allocation itself, right? It's the cleanup.
Yes, the garbage collector.
Ah, the digital janitor.
Exactly. Modern programming languages use a garbage collector to manage memory. It's an automated background process that sweeps through the system's RAM, looking for data that is no longer being used.
So when Ang's code finishes counting that temporary list of 10,000 dummy items, the list is just abandoned.
It just sits there taking up space until the janitor comes by.
And that janitor requires CPU power to do its job, right?
Huge amounts of it. It has to pause other operations, scan the memory, identify all 10,000 individual unit placeholders, and deallocate the memory they were taking up.
Wow. So the original code is not just slow, it's a memory hog that actively strains the system's resources.
Which is exactly why a refactoring suggestion came into play. The community looked at this memory bloat and offered what appeared to be an expert-level fix.
To streamline the whole operation.
Right. The proposed solution was to replace the list comprehension entirely with a function called fold. It's a strict left fold.
Okay, I want to break down what a strict left fold actually does under the surface, because Ang uses an analogy in the post that completely changes how I visualize this.
It's a really helpful analogy.
Yeah, so the original method, the list comprehension, is like having a giant basket of fruit. You want to know how many red apples are in the basket. So you pick up every red apple, put it into a completely separate second basket, and then you stand over that second basket and count them.
Which requires finding a second basket and doing the work twice.
Right. But this fold method, it's like picking up a red apple from the original basket, and instead of moving it, you just hold a little mechanical tally counter in your hand.
Just clicking it.
You see an apple, you click the counter, click, 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 click. You never move the apples. You never need a second basket.
And the mechanism behind that tally counter in the code is a localized accumulator variable. As the program walks through the original list of text blocks from left to right, hence the left fold, it maintains a running total.
So every time it hits a volume header, it just adds one to the accumulator.
Exactly. There is zero temporary list allocation. The digital janitor can literally take the day off.
Okay, so I've heard Haskell described as a lazy programming language, which sounds contradictory for a tool used in high-performance environments.
It does, yeah.
I'm assuming that laziness plays a massive role in why this specific tally counter function is so highly recommended.
It is the defining feature of the language, actually. In a lazy language, if you tell the computer to do a complex mathematical equation, it does not actually do the math right then.
It procrastinates.
It completely procrastinates. Instead of calculating the answer, it builds a data structure in memory called a thunk.
A thunk. That sounds heavy.
But it is. It is essentially a localized IOU. If you ask it to add 1 + 1 + 1, it doesn't give you 3. It stores an IOU that says, I promise to add these 3 ones together whenever you absolutely demand the final answer.
But wait. If we are clicking a tally counter thousands of times for a massive novel, and the system is just writing IOUs instead of actually doing the math, wouldn't that create a mountain of IOUs?
Yes. It creates a massive memory space leak. A thunk takes up way more memory than the actual calculated number.
Oh, wow.
If you build up 10,000 IOUs, your system will run out of memory and crash just trying to remember all the math it is supposed to do later.
Okay, so how does this new expert code avoid the mountain of IOUs?
That is where the apostrophe at the end of fold comes in.
The little tick mark.
Yeah. In Haskell, that signifies that the function is strict. Strict is the exact opposite of lazy. It forces the compiler to abandon procrastination and evaluate the math immediately at every single step.
So when it sees an apple, it doesn't write an IOU.
Right. It actually updates the integer in memory on the spot.
Looking at the post, there is one more detail in this expert fix that seems small, but clearly carries a lot of weight. In the new code, they explicitly tell the tally counter to start at 0, but they write it out as 0::int.
Yes, 0 int.
They are forcing a specific type of 0.
This gets to the absolute micro level of optimization. If you just hand the Haskell compiler a standard 0, it defaults to a data type called integer. In this language, an integer is an arbitrary precision number.
Meaning it can grow as large as it needs to?
Exactly. It can hold a number with millions of digits. That flexibility is incredibly powerful for complex mathematics, but it comes with a structural overhead.
Like, it takes more work to manage.
Right. It requires complex memory management to allow that number to dynamically expand. By writing int, just int, you are instructing the compiler to use a fixed-size, machine-level word.
It's like saying, just use the basic hardware counter, don't give me the fancy expanding math module.
Exactly. It bounds the number to the physical limits of the processor's registers. It is constrained, but it is lightning fast and requires virtually zero memory overhead.
So synthesizing all this, the expert fix is doing everything perfectly on paper. It uses a strict evaluation to prevent those heavy IOUs.
Check.
It ditches the temporary list to save the garbage collector. It even hyper-optimizes the specific data type of the 0 to save processor cycles. I mean, it is a theoretical masterpiece.
It really represents every best practice in the optimization playbook.
But here is where the theory hits a concrete wall. I want to describe what this new optimized code actually looks like on the screen, because the original code was basically a single, clean sentence.
Very elegant.
It just said length, and then gave a basic filter for the volume headers. I could read it in 2 seconds.
It was highly declarative.
Now, I'm looking at the visual footprint of this new tally counter code, and it is a complete monster.
That was brutal to read.
We have gone from a single sentence to a dense, nested paragraph full of special characters. There are lambda expressions with arrows pointing everywhere. There is a manual case statement doing manual pattern matching. There are explicit accumulator variables.
It forces the human reader to parse the raw mechanics of the loop rather than the intent of the logic.
As someone who has to maintain complex systems, I would look at this and immediately ask, is this extreme loss of readability actually worth the performance gain?
It's a fair question.
I mean, when you come back to this project in 6 months, you are going to have a migraine trying to reverse engineer what this dense block of symbols is even trying to accomplish.
The readability versus performance trade-off is the oldest battle in software engineering. We often accept that ugly, complex code is a necessary evil for top-tier speed.
But Aang actually put this to the test, right? Aang ran a benchmark evaluation to see just how much faster this unreadable, hyper-optimized tally counter really was. And the results are the biggest twist of this entire deep dive.
The benchmark numbers don't lie.
Without explicitly forcing the compiler to aggressively optimize things in the background, this new foldl code, the theoretical masterpiece, actually performed much worse than the original code.
Yep.
The manual tally counter was slower than moving all the furniture across town into a new house.
Which shatters the entire premise of the refactoring suggestion. We just spent all this time outlining why memory allocation and garbage collection are massive bottlenecks.
Right.
And yet, avoiding them manually somehow created an even bigger bottleneck.
I am genuinely confused by this.
Okay.
If we remove the heavy temporary list and we force the math to happen instantly to avoid the IOUs, how on earth is it slower? Did Aang just write it wrong?
So Aang notes in the post that the deep technical breakdown of why it was slower will be covered in a future follow-up, part 202.
Okay, so a cliffhanger.
A bit of one, yeah. But we can actually theorize exactly what is happening here based on how modern compilers function. It comes down to something called compiler optimization rules, specifically list fusion.
List fusion. What is the compiler fusing?
Think of a compiler not just as a translator, but as an incredibly advanced artificial intelligence dedicated to making your code run fast. Over decades, the creators of Haskell have programmed the compiler to recognize common idiomatic patterns.
Like building a list just to find its length.
Exactly. When the compiler sees standard, simple code, like a basic list comprehension followed by a length function, it has a built-in rule for that.
Oh, wow.
It essentially says, I see what you are trying to do here. You are building a temporary list just to measure it. I know that's inefficient, so I am going to secretly rewrite your code in the background into a highly optimized tally counter.
Wait, so the simple original code was already being converted into a tally counter behind the scenes?
To a degree, yes. The compiler can automatically fuse the creation of the list and the consuming of the list into a single efficient loop. It literally optimizes away the intermediate list.
So why did our manual expert tally counter run slower?
Because when you write a dense custom loop full of manual lambdas, explicit accumulators, and strict evaluations, you break the compiler's ability to recognize the pattern.
The compiler looks at that dense paragraph of symbols and says, I have no idea what you're trying to do.
It backs off entirely. It says, you clearly think you are smarter than I am, so I will run this exactly as you wrote it without applying any of my advanced automated fusion optimizations.
That is wild.
By trying to manually optimize the code, the expert actually defeated the compiler's automated optimizations. A custom manual loop written by a human is almost always slower than a standard loop that has been mathematically optimized by the compiler's fusion engine over 20 years of development.
That is a staggering realization. We ruined the speed by trying to be too clever. But this brings up a massive logical gap that we need to resolve.
Okay, what's that?
Well, the original code was still a memory hog that strained the system, right? And this new optimized code is an unreadable mess that performs worse. It feels like we are trapped choosing between two terrible options.
We need a third way. A solution that communicates clearly to the human, but also triggers those powerful automated optimizations in the compiler.
Which is exactly what Aang kept digging for and eventually found. Aang discovered an alternative solution that represents the ultimate golden mean.
Walk us through the final iteration.
So Aang realized you could rewrite the code by combining the best elements of both approaches. Instead of using the length function, Aang used the sum function.
Ah, returning to a highly declarative approach?
Yes. The final code structure looks identical to the very first version. It uses that clean, readable list comprehension syntax. But inside the brackets, Aang made one vital change. Instead of using those empty parentheses, the dummy unit placeholders, Aang just used the number 1.
So the intermediate list isn't filled with empty units, it's filled with ones.
Right. For every volume header it finds, it drops a 1 into the list, and then instead of asking for the length of that list, Aang asks the program to sum the list. Just adds the ones together.
It is brilliantly simple, but we have to address the elephant in the room here.
The temporary list problem.
Yes. Functionally, as a human reading it, it still looks like we are building an intermediate list. Instead of a list of dummy items, we are building a massive list of ones. Aren't we just moving the furniture across town again?
Yeah.
Why wouldn't this crush the garbage collector just like the first attempt?
I was wondering the exact same thing when I read it. If the whole problem was memory allocation, how does building a list of ones solve anything?
This is where that compiler magic we just discussed comes full circle. Because Aang returned to using standard idiomatic functions, a basic list comprehension, and a standard sum function, the compiler instantly recognizes the pattern.
It sees the intent.
The compiler's fusion rules kick in flawlessly. It sees that you are generating a list of ones strictly to sum them together. The compiler automatically intercepts that process and optimizes the intermediate list completely out of existence.
It never actually builds the list of ones in the computer's memory.
Never. The compiler transforms it into a hyper-efficient machine-level tally counter dynamically during the compilation phase. You get the blazing fast performance of the strict left fold, but you never had to write that unreadable monster of code.
So we get to write the simple notepad version of the logic, and the machine automatically translates it into the flawless mechanical tally counter version.
And beyond the performance, look at what this does for readability.
It's incredible. Summing a list of ones maps perfectly to the human concept of counting. You aren't trying to trick the machine with strict evaluations, and you aren't writing a granular instruction manual for how the machine should manage its memory registers.
Right.
You are just cleanly stating what you want to achieve.
That clarity is the most valuable asset in any complex system. When you write code or design a business workflow, you are fundamentally communicating twice.
How so?
Well, you are issuing instructions to a machine or a team, yes, but you are also documenting your intent for the next human being who has to interface with your work.
And quite often that next human being is just you, 6 months from now.
Yeah.
Desperately trying to remember why you built it that way.
Exactly. If your logic is shrouded in manual, overly clever optimizations, your intent is lost.
So bringing this all back to you, the listener. Whether you are coding in Haskell, mapping out a project timeline, or trying to invent a new organizational system for your life, there is a massive lesson here about the seductive trap of cleverness.
We all want to feel smart, you know? Implementing theoretical best practices and complex optimizations gives us a sense of mastery over the tools we use.
But you must always benchmark your assumptions against reality. Just because an expert online tells you that a manual tally counter is theoretically superior to moving baskets of apples, you still have to test it in your specific environment.
Because, as Aang proved, added complexity almost always masks hidden costs.
Right. And the cost here wasn't just a loss of readability. It was a tangible drop in actual performance.
It is a stark reminder that complexity for the sake of optimization is a false idol.
We started this deep dive talking about the illusion of that perfectly streamlined, hyper-engineered highway. The goal of problem solving shouldn't be to build the most technically complex route imaginable. The goal is to get to your destination without your engine catching fire and without getting hopelessly lost along the way.
Which leaves us with a final thought to ponder, building directly on Aang's benchmark discovery. We so often view our tools compilers, project management software, even spreadsheets, as rigid, literal machines that we have to outsmart.
I really do.
We twist ourselves into knots trying to speak their language perfectly, manually managing accumulators and explicit type annotations.
We try to do the machine's job for it.
But what if the ultimate form of optimization isn't writing things the machine understands best? Modern tools are incredibly sophisticated. What if the highest form of optimization is writing things that clearly communicate human intent, trusting the tools to do the heavy lifting?
That's a powerful shift in perspective.
Clarity might just be the most sustainable performance metric of all, because if your system is clear, it can be adapted. If it is a clever, unreadable mess, you are permanently stuck in the mud.
A perfectly optimized system that no human can decipher is just a time bomb waiting to go off. So the next time you find yourself trying to meticulously streamline a problem, take a step back and ask yourself, am I building a better tally counter, or did I just forget how to count? Focus on intent, keep your solutions readable, and we'll catch you on the next deep dive.